specificate of solids. That is classical free electron theory fails to explain the specificate of solids. What do you mean specificate of specificate? It is the amount of heat required to rise the temperature of the substance by 1 degree. That's how we define the specificate. Here CV refers to the specific constant volume. You know that it is a amount of heat required to rise the temperature of the substance at constant volume that is by 1 degree, isn't it? So according to classical free electron theory, when you say, when the substance receives energy, that is thermal energy, each electron now here assumes a kinetic energy of 3 by 2 kT, and that is kinetic energy is equal to 3 by 2 kT. So now in 1 kilomole substance, there are any number of that is, for example, if you take carbon as the substance in 1 kilomole, it is 6 point, that's Avogadro number of atoms, that is 6.026 10 to the power 26 atoms per kilo mole will be there. Okay, so each electron, each atom now gains energy equal to 3 by 2 kT. Each electron in the atom gains the energy is equal to 3 by 2 kT. Therefore, if you have this 1 kilomole of substance, the total energy will be 3 by 2 kT into Na. Therefore, this UT is the internal energy, that is equal to 3 Na kT by 2, that is equal to 3 by 2 RT, where NaK is R, that is the gas constant, therefore it is 3 by 2 R. Therefore, this internal energy of 1 kilomole substance in a substance is equal to 3 by 2 RT. Okay, so now if you calculate a specific heat at constant volume, that is CV is equal to dUT by dt, specific heat at constant volume is equal to 3 by 2 R. Experimentally, it was found that 10 to the power minus 4 RT, and according to the experiment, it is function of temperature also, numerical value. It is not 3 by 2 here, it's 10 to the power minus 4. It's very small quantity. There is a huge difference in the specific heat with respect to the theory and as well the experiments observed. Therefore, you see that this classical free electron theory fails to explain the specific heat. The conductivity, if you make use of this classical free electron theory, the conductivity in a conductor based on classical free electron theory is directly proportional to inverse of root of T. Sigma, according to theory, proportional to 1 by root of T. But experimentally it is found that it is not the 1 by root of T, it is simply 1 by T, proportional to 1 by T. There is a mismatch of experimental observation and the this theoretical classical free electron theory. Therefore, there is a difference. This difference cannot be explained. The experimental observation of the that is proportional 1 by T cannot be explained by the classical free electron theory. Therefore, this is another failure of the classical free electron theory. So, the second failure is that it is not able to explain the temperature dependence of electrical conductivity. According to classical free electron theory, it is conductivity is inversely proportional to root of T, but experimentally observed it is proportional to 1 by T. It is not 1 by root of T. This is the observation. And next one, that is according to classical free electron theory, sigma is equal to Ne square tau by m. So sigma, the conductivity is proportional to n, that is the charge concentration. Sigma is proportional to charge concentration. According to classical free electron theory, the conductivity sigma is proportional to charge n, that is sigma proportional to n. But if you look at the table here, where n refers to the charge concentration, see the first metal in the table, copper, the valence is 1, the charge concentration, that's n to the power 10 to the 28, it is equal to 8.45 into 10 to the power 28. Okay, it is plus 28, you make this is plus 28. And for silver, the valence is 1, and the number of charge carriers per unit per unit volume 5.85 into 10 to the power plus 28. If you look at the zinc, which is got the valency 2, it is 13.10 something, and aluminum, that is valency 3, 18.06. See, look at, as the valence is increasing, the charge concentration is increasing. For monovalent, it was 8.45. For aluminum, it is 8.06. But look at the conductivity. Conductivity copper is 5.88 into 10 to the power 7. And if you look at the aluminum, it is 3.65. See, here the concentration of the charges is not proportional. If you look at it here, the conductivity is not proportional to the charge concentration. The monovalent, which is having less charge concentration, but conductivity is large. If you look at aluminum is trivalent, the charge concentration is more, but the conductivity is less. This is the experimentally observed values. Therefore, according to classical free electron theory, the conductivity should have been directly proportional to n, but it is not so. It is as the smaller the concentration here, larger the conductivity. Here, we can conclude that the monovalent metals like copper and silver, they got the higher conductivity compared to the trivalent or the divalent metals. Zinc is divalent, aluminum is trivalent. So, monovalent conductors are more, they show, exhibit good conductivity, large conductivity compared to trivalent and divalent. This is another failure according to the classical free electron theory. It is not proportional to n, but is different than this. Therefore, classical theory once again fails in explaining the dependence of conductivity on electron concentration. So now, because of these failures under classical free electron, another theory was put forward by Sommerfeld in the year 1928. This theory and understanding is based on the quantum physics. Therefore, it is called the quantum free electron theory. So now some of the assumptions are made here once again by Sommerfeld. The electrons travel. The electrons travel in a constant potential inside the metal, but stay within the boundaries. This is again similar to our classical free electron theory. And coming to the second assumption, the mutual repulsion between the electrons and the attraction between the lattice and the electrons are ignored. They are very small. So this is again a similar same assumption that was there in the classical free electron theory. Look at the third assumption. The energy values of conduction electrons are quantized. There in classical free electron theory, the energy values of the electrons can be any value, any arbitrary value it can take up. According to quantum mechanics, the energies of the electrons cannot be any value. It is, they are the discrete values. Therefore, the energy here is quantized. This is different from classical free electron theory. And the fourth one, the distribution of electrons in various energy levels will follow according to the rules of Pauli exclusion principles and obeying the FD, that is Fermi-Dirac statistics. The first two assumptions here, number 1 and 2, they are same as classical free electron theory assumptions, but third and fourth are different from the classical free electron assumptions. So, the new assumptions under classical free electron theory, that they are the energy values of conduction electrons are quantized, and the distribution of electrons into various energy levels follow the Fermi-Dirac statistics. These are the new assumptions. These were not there in the classical free electron theory. So I'll listed out the difference, the major differences between classical free electron theory and the quantum free electron theory. The first column is quantum free electron theory. Second one is the classical free electron theory.